So, photoconductors' resistance decrease as temperature or light intensity increases is explained. As temperature increases in photoconductors, more quanta of energy is similarly provided to the electrons, and more electrons are excited to the conduction band, and hence more holes are created. This increase in charge carriers allows more current to flow when an electric field is applied across the semiconductor, decreasing its electrical resistance. In contrast, conductors like metals' resistance increase as temperature increases, as it causes electrons to vibrate in the metallic lattice and obstruct current. Examples of elemental semiconducting materials would be silicon and germanium. Each semiconductor atom has 4 valence electrons, and each semiconductor atom is bonded to 4 other such atoms in a crystal structure. This lattice structure results in the band and energy gaps as discussed above in semiconductors. Originally, germanium was the primary element used in semiconductors, as silicon was much more difficult to purify. However, once methods were developed to purify silicon from sand and other materials, it was not only cheaper to produce, as it was much more abundant in the Earth's crust, it could also withstand higher operating temperatures without melting or malfunctioning. Silicon hence replaced germanium as the most common semiconducting material. Next, I will talk about intrinsic and extrinsic semiconductors. As mentioned by Britney Spears' Guide to Semiconductor Physics, when a semiconductor produces electrons in the conduction band and holes in the valence band, naturally through heat or light, it is known as an intrinsic semiconductor. No doping of the crystal lattice has occurred, such as in silicon or germanium. However, if a small amount of impurity, like boron or phosphorus, is added to the crystal lattice, it modifies the substance's electrical properties. This is known as doping. Doping produces either N-type or P-type semiconductors. In P-type semiconductors, an element with 3 valence electrons, or group 3 element, is added to the crystal lattice, and this produces 1 electron deficiency in the lattice structure. An additional hole has effectively been created in the semiconductor structure without exciting an electron to the conduction band, and it acts as a positive charge carrier that can carry current. Conversely, N-type semiconductors are produced by doping it with a 5 valence electron element, or group 5 element. This produces an electron in the crystal lattice that is elevated to the conduction band. The dopant has hence produced an electron or negative charge carrier free to move through the semiconductor without needing higher temperatures or light to excite it to a higher energy band. P-type semiconductors have more positive holes that can carry current than electrons, while N-type semiconductors have more negative charge carriers or electrons than positive holes. It is important to note that even in P-type and N-type semiconductors, both holes and electrons are present. But in P-type semiconductors, the holes, the positive holes, are the majority charge carriers, while in N-type, the negative electrons are the majority charge carriers. Semiconductors are awesome because they can be used as solid circuits without the need for a fragile vacuum glass tube or thermionic emission. Oh snap would probably be appropriate and common slang today if thermionic devices were used today. Thermionic devices included valves and triodes, which contain 2 or more electrodes in a glass vacuum tube. They rectified or amplified current in devices. Solid-state devices included diodes, which also rectified current, but used much more hardy semiconductor layers to do so, and transistors, which amplified current. To illustrate, the semiconductor diode is a device that, like a valve, rectifies current. It only requires 1 P-type and 1 N-type semiconductor to work. When the current flows from the P-type to N-type semiconductor, the electrons and holes move towards the center of the diode and cancel each other out in an electron-hole recombination. In contrast, if current does not flow in the forward bias direction, but rather in the reverse bias direction, the holes will move towards the P-type semiconductor and the electrons towards the N-type semiconductor, creating a depletion zone where current cannot flow. Thermionic devices were not only more fragile than solid-state devices, they produced much more heat, had a shorter lifespan as they reacted with the gas in the tube during emission or just melted, had slower switching speeds, required very high voltages compared to solid-state devices to bias things to correctly rectify signals, and would not work once air was let into the vacuum tube. They also required a separate heating circuit and were overall less energy efficient than semiconductor devices. With all their disadvantages, it is hence unsurprising that thermionic devices were replaced by solid-state devices. Solid-state devices were not only much more durable, lightweight, and efficient, they can easily be mass-produced and formed into a single integrated circuit that consists of thousands or millions of diodes and transistors, all on the 2mm microchip. It was these shortcomings of thermionic devices, reduced efficiency, increased heat production, slower switching speeds, higher fragility, and shorter lifespan that prompted people to research into alternatives to thermionic devices to improve communication technologies. Once solid-state devices were invented, they hence replaced many thermionic devices in society. Transistors are an example of a solid-state device that has replaced thermionic triodes and are now used in microchips and microprocessors in the form of integrated circuits and have allowed the miniaturization of technology. They allowed faster transfer, processing, and storage of information, all in a 2-gram microchip, and this meant complex tasks could now be performed and controlled using microchips in a variety of machines, cookers, toasters at home, and assembly machines in the industry. Tedious tasks previously carried out manually could now be carried out using a single microchip computer. At the same time, the increased storage and processing capabilities of microchips and computers has led to the development of the internet and advances in medical, entertainment, communications, and other industries. Bulky, heavy devices that relied on bulky, heavy thermionic valves and circuits could be replaced with streamlined, lightweight microchips, allowing the creation of many pocket devices like our important iPods and thumb drives. It is hence safe to conclude that the invention of transistor microchips has improved our quality of life by allowing more free time and improving our technology and industry, as well as allowing the invention and production of what many would now term essentials.